All right, so today we're just going to talk about exponential functions. No calculus today. Review of exponential functions. So that Monday we can talk about the derivative of the exponential function. All right, so let's suppose we start with an air freshener that has 30 grams in it, and it evaporates over time. We want to write a formula for the quantity Q grams of air freshener remaining T days after the start if we decrease by 2 grams a day. So formula Q remaining T days. So Q after T days would be what if we decrease by 2 grams a day? 30 minus 2T. Start with 30, subtract 2 grams every day for T days. So what kind of function is that? Linear. Good. All right, now if I want to decrease by 12% per day, I'm going to change my formula to be Q of T equals what? That is if it said it's reduces by a continuous 12% per day. If it's just, 12% flat at the end of each day, we would say, okay, well, we start with 30 grams. And if you decrease by 12%, how much do you get to keep? 88%. 88%. So you have times 0.88 to the T. That's how much we have left. All right, so exponential functions are of the form P naught times A to the T. P naught is your initial quantity. A is your base. We're going to insist that A be positive and not 1. Because if A were 1, what kind of function would Q of T be? That's at 30 times 1 to the T. It'd just be 30, yeah, because 1 to the anything is 1, and it'd just be constant. So A can't be 1, or it's not exponential. What if A was negative? No, what causes decay is when this base is less than 1. So this is decay as it is, right? But if I had that base be negative, for example, 3 times negative 2 to the T, it would oscillate because when you have an even power be positive, an odd power be negative, so you'd end up with something oscillating like this, getting bigger and bigger. So it wouldn't be exponential growth, or what we want to think of as exponential growth. Right, so we insist that A be positive and not 1. When A is bigger than 1, we have growth. Think of that as more than 100%, keeping more than 100%. And if A is between 0 and 1, then we have exponential decay. So what happens to P of T in that function each time we increase T by 1? Yeah, not the calculus of it, not the slope of the tangent line, just the value of P of T. What happens to the value of the output when you increase the input by 1? Yeah, it changes by a factor of A. Because if this went from A squared to A cubed, we'd multiply by A. Yeah. So P of T changes by a factor of A. And I'm writing changes as opposed to increases because if A is less than 1, it's going to decrease. All right, let's fill in some basic properties of exponential functions. We're going to graph 2 by plotting points that correspond to t equals 2, 0, and -1. And then we're going to use these 2 examples to draw some general conclusions about exponential functions, which is generally sort of a bad practice in math to do 2 examples and then draw conclusions, but that's what we're going to do today. All right, so 3 to the t. So if I plug in 0, 3 to the 0 is 1. If I plug in 2, 3 squared is 9. And when I plug in -1, 3 to the -1 is a third. And I get this sort of general looking exponential growth function. And then for 1/2 to the t, plug in 0, I still get 1. If I plug in 2, 1/2 squared would be a fourth. If I plug in 1, that's a half. If I plug in -1, I get what? 2. So I get a function that looks like this. All right, so using these 2 pictures, what's the domain of an exponential function? What x values does it live on? All real numbers. What about its range? Non-negatives, just positives, yeah, because it doesn't ever actually get to 0, yeah. So one way of saying positives is to put the symbol for real numbers with a little plus. Or we could use interval notation and write 0 to infinity. All right, intercepts. X or y intercepts, are there any? No x-intercepts because it always stays above 0. Y-intercept, 1 in both the growth and decay. Right, yes, because these are both 1 times 3 to the t and 1 times 1/2 to the t. So yeah, we could think of this as y equals p naught. Yeah. Asymptotes. Y equals 0, the x-axis. Increasing and decreasing. Yeah. So it's always either increasing or decreasing depending on the base. And concavity? Always up. All right, so we want to go back and sketch the graph of -2 times 3 to the t on the same axes. What? If the base is negative? A is the base, right? Yeah. We established earlier that we always insist that A be positive. Okay, so now I want to sketch -2 times 3 to the t. So if I plug in 0, I get -2. And if I plug in 1, I get -6. And plug in 2, -18, that goes off my graph. -1, -2/3. So it's going to look like this. All right. Does that mean that any of my properties were wrong? It wasn't concave up. It was decreasing when the A value was positive. The range was negative reals. So are my properties wrong, or can I think of this another way? Yeah. Yeah. So we can think of this as a transformation. If we insist that the initial amount be positive, because usually we use exponential functions to model real things like growth and decay in the real world, which means you wouldn't be starting with a negative amount. So we can think of that negative sign more as a transformation of an exponential growth function. So we should insist P naught be positive, and then we can treat -2 times 3 to the t as a transformation. So, okay, let's look at the end behaviors of the 3 exponential functions we looked at. So the limit as x goes to infinity of, let's do 3 to the t. What's its end behavior as you go to positive infinity? Infinity, it just gets bigger and bigger. All right, how about the limit? Oops, I should have used a t. The limit as t approaches negative infinity of 3 to the t. 0, yeah. For 3 to the t, as I approach negative infinity, as my x's approach negative infinity, my graph, the y values are approaching 0. Okay. How about the limit as t approaches infinity of 1/2 to the t? 0. And the limit as t approaches negative infinity of 1/2 to the t. Infinity. And then we have one more function, the limit as t goes to infinity of -2 times 3 to the t. I don't remember. Let's see. Yeah, as we approach infinity, that goes to negative infinity. And as we approach negative infinity in t, my y values approach 0. So there are certain kinds of modeling problems that typically lead to exponential growth or decay, including population growth, radioactive decay, medication levels, and compound interest. So let's say we want to write an exponential function that models a population of ladybugs that starts at 150 and triples every month. What kind of formula would I use? (150 times 3 to the t). Yeah, so I would say p of t equals p naught times a to the t. My p naught is 150. That's how many I start with. A is my growth factor, which is tripling, so that would be 3 to the t. And then I should put a little note, t in months. All right, if we have a dinosaur bone that originally contained 32 grams of carbon-14, And the amount of carbon-14 that remains in an organism once the organism dies is known to get cut in half every 5,730 years. So if I write down my function here, P naught times A to the T, what's my P naught? How much am I starting with? 32 grams. And then how am I changing the size? What's my growth or decay factor? 1/2. 1/2. So I could just say to the T and measure T in sets of 5,730 years. But that's kind of weird, right? So how could I put up here the number of sets of 5,730 years that have passed? Yeah, if I measure T in regular years, I would like 10,000 years, right? Divide by 5,730, and that tells you how many sets of 5,730 have passed. So in this one, we'll measure T in years. All right, how do we figure out P naught and A? So P naught is always your initial amount, which happens to be your y-intercept, right? So P naught is initial amount, right, which is the amount you have at time 0, which means it's the y-intercept. Okay, so we've got the y-intercept. To get A is our growth factor. Which tells us, or decay factor, right, which tells us how the function changes. So we know how much we start with and how it changes, which is very similar to a line, mx plus b. B is how much we start with, m is how we change, how it grows. It's just that at every step in a line, you grow by a certain static amount, and at every step in a exponential, you grow by a factor instead of a constant amount. And so the process for finding the equation of a line, first find the slope, then plug in a point to get the y-intercept, is really similar when you're working with an exponential. You want to find an exponential between 2 points. First find the growth factor, and then plug in a point to get the y-intercept. So let's say y equals a times b to the t, random letters. Okay. Maybe we'll stick with our same p naught times a to the t. Okay, so I'm going from 0,5 to 115. So my t values increased by 1. How did my y values change? Times 3. Yeah. So if I was trying to figure out the equation of a line, I would say, oh, it increased by 10, right? But when I'm trying to fit an exponential here, I want to know what factor it increased by. So I'd say, well, 5 times 3 is 15. So that's going to be my growth factor, because I did a step of 1 in x, factor of 3 in y. So I say, okay, that means that p of t equals p naught times 3 to the t. And then in this case, I can just plug p naught in because they gave me the y-intercept. What is it? 5, right? The y-intercept is the y value when the t value is 0. So I've got p of t equals 5 times 3 to the t. So that was kind of easy. What made it easy was that they had the step increase for t was just 1 unit. So it was easy to figure out the growth factor, and they gave the y-intercept. So this one's a little bit harder. P of t equals P naught times A to the t. So the first thing I want to figure out is my growth factor A. So if I make myself a little table here, and I have t, P of t, I know that if I put in 2, I get 10. And then I've got 3, 4, 5, I get 30. So I need to figure out what number I multiply by to move from one step to the next, so that when I get to step 5, I get 30. So if this were a line, if this were slope, I would see what my total change was, right? And then divide by the number of steps. Okay, how would I do it to figure out the factor? What factor I should multiply by there? Where's 20 coming from? Oh, so that's a 30 minus 10, the 20 is giving you total change. But I want to know what factor. What factor did I grow by? What did you multiply 10 by to make 30? 3. Okay, so to do the whole step, if I was going to jump from one to the next, I did times 3, right? But I need to make smaller steps. So think about what you do with a line. You figure out the whole change, the 20, and then you divide by the number of steps. Here I'm doing the whole growth factor times 3. How do I figure out what each of the smaller steps are? Divide 30 by 5. That would give me 6, right? If I multiply by 6 at every step, I get 60, 360. 360 times 6 is something huge, right? I need to figure out what do I multiply by so that I can do times this thing, times the same thing, times the same thing, and I go from 10 to 30. X to the third. Right, what number is, that's the question. What number am I multiplying by 3 times to get from 10 to 30? I could multiply by 3 once, or what number 3 times? If I multiply by 5 3 times, I go, okay, 10 times 5 is 50, 50 times 5 is 250, 250 times 5 is 1250. It's got to be smaller than 3, right? Yeah, 1 wouldn't work because it would be 10 times 1 is 10, times 1 is 10, times 1 is 10. 2, 10 times 2 is 20, times 2 is 40, times 2 is 80. It's not 2. Ah, okay. So 10 times what cubed equals 30? 10 times what times x times x times x. We're multiplying by the same thing 3 times. We're getting 30. So x cubed equals 3. So what's x? The square root of 3. Okay, so I have P of t equals P naught, still don't know what P naught is, times radical 3 to the t. All right, how do I figure out P naught? Plug in a point. I could plug in 2 for t and 10 for P of t, solve for P naught. But I'm out of room. I'll go on another page here. Oh, the cube root. Yes, you're right. Yeah, it's the cube root, not the square root. Thank you. Silly. All right, so I plugged in 2 for t and 10 for y. Just like you do when you're finding the equation of a line. Once you know how it grows with the slope, or once you know its growth factor, plug in a point for x and for y and solve for the y-intercept. So let's see, root 3 squared. We'll just call that 3 to the 2/3, and then divide both sides by that. Can we make that look any simpler? I could. That's good enough. 10 over 3 to the 2/3. I could get a decimal, yeah. Oops. Not the problem. Can I simplify that? I have a 3 to the 1/3 on top and a 3 to the 2/3 in the bottom. Can I simplify? Yeah, can I make it 3 to the negative 1/3 instead? Somebody better stop me. Yeah, you can't because of the exponent, right? The order of operation says you have to do the power first. So I can't do anything with this multiplication, simplifying, until I plug in a t and do the exponent first. All right, good. So note that the base a of an exponential function has a lot to do with the growth rate that we call r. So I've been calling it the growth factor. When you put it right in the equation, it's the growth factor. But we like to give things growth rates, like percentages. So in this equation, 50 times 1.04 to the t, what's my growth rate as a percentage? 4%, right? So you would read that growth factor as 1.04, and then you would say that's like the 1 is representing the fact that we get to keep 100% of what we have, and the 0.04 is an added 4%. Yeah, that would be a common mistake. So 104% is what you get to keep. You get to have 104% of what you had before, which represents a 4% increase. Yeah. All right, how about in B? What's my growth rate? Yep, 27.6%. And in C, 8% decay, because this 0.92 means that we're keeping 92% of what we had, which means we lost 8%. Sure. So you can write negative 8%, or you can write 8% decay. Writing both the negative and the word decay is like using a double negative, and would technically mean 8% growth, right? They cancel each other. So avoid that. Okay, so now instead of writing exponential functions as p naught times a to the t, which uses base a, we could instead use base e and write it as p naught times e to the kt. And this equation is used whenever you see the phrase continuous growth or continuous decay. So before we move on here, I just want you to see that they are equivalent. For any p naught times a to the t, you can make it equal p naught times e to the kt. Okay. So we can always write a function either way. And there's a p-naught on both sides of these equations, right? And on the right, I could write this as e to the k to the t. Because when you raise a power to a power, you'd multiply the exponents. So for those two things to be equal, a would have to equal e to the k. So this is how you convert from one form to the other. Your growth factor a equals e to the k, and k is called your continuous growth or decay rate. A is your growth factor. Okay, so what is this number e? Well, let's look at our calculator for a minute. And we're going to estimate this limit 1 plus x to the 1 over x as x goes to 0. All right, so I just type it in. 1 plus x. What's happening? Oh, there we go. 1 plus, parentheses, 1 plus x to the parentheses 1 over x. And I'm going to look at my table, and I'm going to plug in smaller and smaller values for x. So this is not a derivative, just a limit as x goes to 0. No h's involved. And I'm just going to plug in small x values. And I'm getting numbers that look like 2.718. That is e. The definition of e is the limit as x goes to 0 of that expression. So that is why in all of your previous math classes, when you've studied exponential growth, continuous compound interest, we've never been able to explain where the number e fully comes from, because you need to understand a little bit of calculus to get that number. Okay, so now we're going to rewrite the equation for e to the 0.5t in the other form, p naught times a to the t. So what I showed you before is that a equals e to the k is how we convert. A equals e to the k. And k in this case is 0.5. So a equals e to the 0.5. And we could get a decimal. E to the 0.5. About 1.64, 1.65. So when I write it in this form, what's my p naught? 4. It's the same in both expressions. 4 times 1.65 to the t. Okay, so when I look at this, what is my continuous growth rate for this function? 0.5 or 50%, right? So continuous growth rate equals 50%, right? That 0.5 represents 50% continuous growth rate. What is my just plain old, like yearly or whatever t represents, growth rate? 65%. This is kind of like the difference between APR and APY, right? So if your bank is compounding interest continuously, you would use the 4e to the 0.5t, and you would say that the APR, the APR is 50%. I'd be lucky, right? But you say the APY, which is your effective yield, what you actually make in a year, would be 65%. Yeah. I'm not gonna like test you on those terms. I'm just trying to like connect it to something else. All right, if I can also switch back the other way, I want to go from P naught times a to the t to P naught e to the kt. So I would use my same equation, a equals e to the k. But in this case, I know a, right? A is 1.04, and I need to figure out what k is. Anybody remember how to solve that equation? The natural log, yeah. So we can't finish it without using the natural log, which is a tool that we're going to review in a few classes. But if you happen to remember it, you take the ln of both sides, and the ln of e to the k is, it's just k, yep. Or you could think of it as k times the ln of e, but the ln of e is just 1. Right? So k is the ln of 1.04, which we can get from our calculator. .03922. So my final equation would be P of t equals P naught, which is 50. It stays, P naught's the same in both equations. And then e to the 0.03922t. So this one makes a little more sense to talk about in terms of bank interest. This 1.04 corresponds to a growth factor of 1.04, which is what rate of growth? 4%. So that's a discrete 4%. At the end of the year, you get 4%. Right? But over here, we have 0.03922. That represents a continuous growth rate of 3.922%. Pretty close to 4%. It's a little bit smaller because when you compound continuously, you make money on interest, and we can lower the rate a little bit and have the same effective yield. So in this case, if you're interested, if the bank's compounding continuously, you would say 3.922% is the APR, the advertised rate. 4% would be your APY, your yield, your yearly yield. Does that make sense? Okay.